In today's mini lecture, we are going to talk about the rotational equivalent of Newton's second law. We're also going to talk about angular momentum and rotational kinetic energy to wrap everything up. Now, what I haven't really talked about is that actually angular velocity and angular acceleration are vectors, just like how linear velocity and linear acceleration are vectors. We're not really going to use that vector idea too much for the angular velocities and accelerations, but I still do want to talk about them. So for your angular velocity, the angular velocity represented by the Greek letter omega always points along the counterclockwise axis of rotation, points along the axis of rotation. And in order to figure out the direction of omega, you use your right hand. Okay, so you figure out which direction is your object rotating. Okay, you take your fingers curl around in the direction of rotation, and your thumb points in the direction of the angular velocity. Okay, so in this image that we have here, our direction of rotation is following that red arrow there. And then, so if I take my fingers and curl them around the direction of the rotation of that disk, my thumb points in the direction of the angular velocity, which is up in this case, okay? And alpha also points along the counterclockwise axis of rotation too. So if you figure out your direction for omega, then you can figure out your direction for alpha, which is your angular acceleration. So just with linear acceleration and forces, we had that the force was equal to mass times acceleration, Newton's second law. Now for rotational motion, our rotational equivalent is that the torque equals what we call the moment of inertia times the angular acceleration. So instead of force, we've got a torque. Instead of mass, we have what we call the moment of inertia. And instead of linear acceleration, we have angular acceleration. Okay, so for example, here we have a bicycle that's rotating around the front part of the bicycle here. Okay, this is our axis of rotation. Our bicycle is rotating with some angular acceleration, and there's a force that's being applied here by the hand. That force applied by the hand is giving that object some angular acceleration, and we can calculate that angular acceleration by figuring out what the torque is from this force and setting it equal to the moment of inertia of this tire times the angular acceleration. So the moment of inertia is a quantity of any object that's executing rotational motion. That's sort of the rotational equivalent for mass. An object's moment of inertia depends not only on the object's mass, but also on how this mass is distributed about the axis center, about the rotation axis center. So the moment of inertia of a collection of a bunch of particles is just going to be the sum of that particle's mass times their distance from the rotational axis squared. So whatever that object is, it has a bunch of mass particles. You figure out all those mass particles, you get the mass of those individual particles, you figure out their distance from the rotational center, you square that distance, and that's the moment of inertia, sum of all of that. So the moment of inertia of any system is equal to the sum of all the individual mass pieces times their distance away from the rotation center squared. Okay, so for example, here we have a rotating disk that has a moment of inertia of its own. And then we have 4 people on the edge of that rotating disk. So the moment of inertia of the system is going to be whatever the moment of inertia is of the disk itself, plus the moment of inertia from each of these individual persons sitting on the edge. That moment of inertia is going to change when those people move toward the center of the rotation axis because the distribution of masses changes in that case. So when these people are further out, this object has a greater moment of inertia. So for the moment of inertia of this system, we've got the moment of inertia of the disk itself, plus the moment of inertia of each of these individual people, which is going to be their mass times their distance away from the center squared. So you've got moment of inertia of the disk plus m of this person, mass of this person, times r squared plus mass of this person times r squared plus mass of this person times r squared, and so on. So whenever those people move closer to the center, you're going to reduce the total moment of inertia of the system, because now the moment of inertia of the disk itself is the same, but these people, they have a different distance away from the center of rotation. That distance from the center of rotation is smaller, so their individual contributions to the total moment of inertia of the system is going to be smaller. So this system here would have a smaller moment of inertia. Larger moment of inertia, it's going to be harder to get the thing to rotate or harder to slow it down. Just like inertia with linear motion. The larger the mass, the harder it's going to get that object to speed up, the harder it's going to get that object to slow down. Now the units of moment of inertia are mass times distance squared, so kilogram times meter squared. Here's what you're going to do for this first engagement check question. You're going to interpret the moment of inertia of a system. So we're going to consider these 4 systems down here and the distribution of objects on a massless disk. To which system will you need to apply the largest torque to maintain the same angular acceleration if the system of masses is rotating? So, okay, well, which system will you need to apply the largest torque if their angular acceleration is the same? So remember, torque is equal to moment of inertia times angular acceleration. So to figure out which system do you need to apply the largest torque to keep the same angular acceleration, you're going to have to figure out which system essentially has the largest moment of inertia. If angular acceleration is the same for all of these objects, the object that you're going to have to apply the largest torque to maintain that same angular acceleration is the object that has the largest moment of inertia. So essentially I'm asking you, to which system will you need to apply the largest torque to keep the same angular acceleration? That's also the system to which you're going to have the largest moment of inertia. Okay, so you get to evaluate the moment of inertia of these systems. So this disk on top of which these 4 masses are rotating, that disk doesn't go into this calculation. Okay, for A, we have this massless disk, and so the disk moment of inertia doesn't go into it. But you have these 4 masses. And the moment of inertia, remember, is the sum of the individual masses times their distance away from the rotational center squared. So for each of these systems, you're going to have to find what is the mass and how far are they away from the center rotation axis squared. Okay, so to find the moment of inertia of this first system, you're going to have to take this mass times its distance from the center squared of rotation squared, plus this mass times its distance from the center of rotation squared, plus this one, okay? Plus this one's mass times r squared, plus this one's mass times r squared. So you're gonna have 4 masses times r squared for this one. And then you're gonna do that calculation for each of these. The r will change and the mass will change. So essentially you're gonna find which one of these systems has the largest moment of inertia. That's the one you're going to have to apply the largest amount of torque to in order to maintain the same angular acceleration. We can piece together the angular acceleration of a system by looking at the sum of the mass times r squared of all the particles. But we can also look at a chart in order to give us the moment of inertia for a bunch of different shapes. This is also a table that's in your textbook, so you can look at that table in your textbook. So for example, here at the top, we have a hoop that's rotating around a central axis, okay? The central axis is in here and the hoop is rotating around it. So the moment of inertia of this object is gonna be its total mass times its radius squared, okay? And then let's say, let's go with this one down here. We're gonna see this one in another problem. We have a long, thin rod with a length of L, okay? And it's going to rotate about an axis through one end perpendicular to its length. So it's going to rotate about this axis. This is its rotational point. And so it's going to make a big sweep around this central axis right here, okay? And as it does that, its moment of inertia is going to be its mass times this length squared divided by 3. So 1/3 ml squared. So here we have a solid sphere rotating around any diameter. Its moment of inertia is 2/5 its mass times radius squared. So whatever the object is in question in the system, you can always come here to this chart and look up what should the moment of inertia be. You might have to add some moments of inertias together for different unusual systems. And if you're thinking about something as a point mass, its moment of inertia is always its mass times r squared. So where r is the distance that mass is sitting away from the rotational center.